Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome everyone to this session of CHE 409 PC6 data analysis. Actually, PC6 involves temperature, flow rate and level control using computer. We just try to have we have two objectives, which one is to evaluate the parameters for tuning PID control loops using Ziegler-Nicholas tuning criteria. The second is to demonstrate the response of a system to various step inputs. So it has 4 sections, the experiment, as you have seen in the demonstration video. 2 of the sections are just observation, and the remaining 2 are the ones that we record the data and then we do analysis of the data. So let me discuss the 2 that involves the demonstration only. One of them, which is the first one, we just try to set the system under integral control or integral and derivative, and then we put a particular set point, for instance 80, and then we set the system going. What we want to do is we want to see how the level of fluid in the process tank is changing with time, and that is it. The second, what we want to do is, the second aspect is we are going to put the system to make the we are going to fill the process tank to 100, and then we subject it to some step disturbance, meaning that from 100, which is completely filled, we drain it to 80, and from 80 we drain it to 70, from 70 we drain it to 40, and that is a step disturbance. And what we want to observe actually is to see if the system is going to have some offset, which actually it does, as we have seen from the demonstration video. So, which is basically the difference between the set point and the measured value. But the other two which involve us to record the data and do the analysis are the one we mainly focus in this our session. The first one involves us to put the system under PID control, which we uncheck the integral and the derivative, and then we select a particular proportional gain. We select 1, 3, 5, 7, 11, like that. That is odd numbers. What we want to do is, at each of those proportional gain, we want to see whether the system is going to become permanently unstable, and at that point where we have permanent instability of the system, the PG corresponds to the ultimate gain, which is the KCU, and then we try to evaluate the period at that proportional gain, which is the KCU. So the data, the raw data, is going to be of this format. For instance, when PG is equals to 1, this is the data we obtain. You can see the set point is around 1.5, and this is the measured value. You can see that we have some oscillation at the beginning, but then it dies out, and this difference between the set point and the measured value is the offset. So it means we have to change to the next one, which is 3. PG equals 3. You can see that the offset becomes minimized, which is the difference between the set point and the measured value. But then we can see some oscillation at the beginning, but then it dies out. Then we go to 5, still the same, and then we go to 7. You can see we have some oscillation, but then around 16 seconds the oscillation begins to die out, to damp. And then we have at PG equals to 7, it means the system is still stable at around 40 seconds here. Yeah, so it means we have to try PG equals to what? 9, which is the next one. So you can see at PG equals to 9, yeah, we got some oscillation up to around 35 seconds. But then before reaching 40 seconds, the oscillation now begins to damp, and then it means this is not actually a point of permanent oscillation. So it means we have to try the next one, which is 11. Luckily, at 11 you can see that within the time reference, which is 40 seconds, we have the system permanently unstable. So it means at this condition, which is PG equals to 11, it means we have obtained permanent instability. And then by implication, the PG now is equals to what? The KCU, which is the ultimate gain. So it means the ultimate gain of this setting, control setting, is what? 11. And now what we want to do is we try to enlarge the scale by taking a lesser time interval of the scale. For instance, we can take between 10 to 15, such that the scale will become a large, so that we can be able to determine the period of oscillation. And this is what we did, and we got this. As you can see, between 10 to 15 seconds, we got these oscillations. Now, still the KCU is 11, and now to determine the PU, which is the period at the ultimate gain, what we need to do is to determine the total time taken divided by the total oscillations. It means the total time taken between 10 to 15 is 5 seconds. And now the total oscillation will be 1, 2, 3, 4, 5, 6 and a half. So dividing the two, now you have your period. This is the first section of the experiment that involves data analysis. The second one is actually, we are going to fill the process tank to around 40%, which means it covers the heater. The heater now becomes fully submerged, and also the thermocouple for temperature sensing is also fully submerged. So from there, we now on the heater to maximum. Then the temperature begins to rise. It means we are subjecting the system to some step change in temperature in a positive direction. So it means it is a positive step change in temperature. So the temperature now begins to rise, and then at the end we have a data of temperature versus time versus temperature. This data, they are the ones we are going to use in our data analysis. So let's go to the business of the day. The first thing we need to do is, from those from method 1, we have PG with the corresponding offset, PG with the corresponding offset, PG with the corresponding offset. So what we need to do is, we should make a table like this: PG, set point, measured value, then the offset. Then we plot the PG versus the offset. This is one thing. Second, we try to determine KCU, which we have gotten as 11. Third, we try to determine the period, which is the time taken per oscillation, which we have done, which will be around 5 divided by 16.5. 5 divided by 6.5. So after doing that, we have this table. We simply fill this table, which is the Nicolas Ziegler's controller setting. So it means for PG, we simply put something like 0.5 times the KCU we got, which is 11. So it means here we have 0.5 times 11. Here it will be 0.45 times 11. Here it will be 0.6 times 11. And then here it will be 0.83 times the period we have obtained. And simply you have finished your data analysis for the first method. Then the second method, you have obtained, if you can recall, time versus temperature. So just plot it, and then you have a curve like this. This is the curve. So this curve has 3 faces, or 3 regions. The first region here, you can see it is actually a curve. But from this point to here, you can see it is linear. And then later on, also it is a curve. So what you just need to do first is to draw a line through the linear region, and also try to intersect the y-axis. And then now you try to draw a tangent to touch the curve at this very place. When you draw the tangent, now this distance between the tangent and the intercept of the line you drew at the linear region is going to be r times l. Let's say you obtain r times l to be 5, and then this interval to be l. Let's say you obtain l to be 2. So it means now r is going to be 5 divided by 2. So it means you have obtained the values of r and you have obtained the values of l. So the next thing you need to do is to determine delta u. Delta u is simply the magnitude of step input divided by total range of possible input. As you recall, we open the heater to maximum, so it means it is 100, and the total possible is 100 as well. So it means we have delta u as 1. So it means by implication, we can be able to fill this table for the control setting. You can see it is delta u divided by r times l, and we have delta u, we have r, we have l. So we can fill the table, and that makes the data analysis complete. What you just need to do is to discuss it based on trying to make some inference and conclusions or deductions. Thank you.